So when you were originally doing Newton's first law, you probably had heard like an object at rest stays at rest. When you did Newton's third law, you did like, all right, equal and opposite reaction. The reason you didn't have an equivalent statement for Newton's second law is Newton's second law has two parts. The first part is that the net force and acceleration of an object are directly proportional. So that's a long sentence to start with. Net force versus acceleration is directly proportional. That's the first half of the law. Second half of the law, and mass versus acceleration is inversely proportional. There's a reason that no one says this as nice, like a nice catchy statement, because all in all, if I had to read Newton's second law in words, it would read net force and acceleration are directly proportional, and mass versus acceleration are inversely proportional. But that's just making observations about things you probably realized in your normal life anyways. Like you probably knew that if you apply more net force, if your forces are even more unbalanced, that makes your object accelerate faster. You already knew that if there's no net force, then there's no acceleration. So we call this type of relationship direct because it's linear, it goes through the origin. Other words for this, like if you are in quick graph also calls this proportional. And it's called proportional because the proportions of this equation are easy to work with. If you double the force, you also double the acceleration. If you triple the force, it'll triple the acceleration. And so on and so on. So if you have 25 times more force, you get 25 times more acceleration. When you do out the equation for this, we would write this as acceleration is proportional to net force. And I'm going to put this in the center for reasons you'll see in a second. Acceleration is proportional to net force. So if you double the force, it doubles the acceleration. If you look at the equations for any of your graphs, you'll notice that net force and acceleration are both in the numerator. Nothing in the denominator yet. On the other half of this, mass versus acceleration. If we look at our three groups for mass versus acceleration, all of their graphs had that nice decreasing slope to asymptotes. That relationship is called an inverse. If mass gets larger, the acceleration gets smaller. The way you can think about this relationships to asymptotes is very light mass objects have large accelerations. Think like a smart car. If you have a little tiny smart car that only weighs 800 kilograms or only has a mass of 800 kilograms, it can accelerate much, much faster than a big, heavy truck. More mass. More mass means that it has more inertia. It's harder to accelerate that object. So then you get less acceleration. Luckily, this equation only has one name. It's just inverse. And what an inverse relationship means is that if mass increases, acceleration decreases. Right? The proportions for this means if you double the mass, you get 1/2 of the acceleration. If you triple the mass, you get 1/3 the acceleration. If you do, 100 times the mass, you get 1/100th of the acceleration you did before. If you look at the equation for this, Notice that it always puts this number in the denominator. So I'm going to put mass in the denominator of this equation. More often, you probably saw F equals ma as Newton's second law. The reason I'm going to write it like this is it's actually going to be mathematically significant to write it like this. This equation says force and mass affect acceleration. Sometimes when people see this as like F equals ma, like when you were little, if you saw it as F equals ma, that is mathematically true, but it's misleading. It's misleading because there could be more than one force, so you have to consider the net force. It's also misleading because this looks like acceleration affects force when it does not. But it's misleading to write it as F equals ma because acceleration doesn't change the force, right? If you have a different acceleration, that doesn't change the forces acting on the object. It's the other way around. So what I figure is I'm going to show you some examples on how to do these problems. Like, how do you use this equation? So be sure to watch the next videos in which we go over how to solve one-dimensional, two-dimensional, and two-dimensional with a force at an angle Newton's second law problems. Best of luck!